So in this problem, we have a straight tunnel which is dug between 2 points on a uniform density spherical asteroid, where the 2 points are separated by an angle theta from the center of the asteroid. And the walls of the asteroid are polished such that a person can slide without friction through the tunnel. Now in part A of the problem, an astronaut starts from one end of the tunnel and slides through the tunnel to the other side. And we're asked to figure out what the speed of the astronaut is when he is in the middle of the tunnel. In part B of the problem, we're asked to figure out how long it'll take for the astronaut to go from one side of the tunnel to the other side of the tunnel. So to simplify the problem, we're going to start with part B. And after figuring out the answer for part B, we're going to figure out part A based on our result from part B. So here is a diagram of the astronaut with a mass little m, and the radius of the asteroid is going to be given by big R, and let's call the total mass of the asteroid big M. So little r here is the radial vector from the center of the asteroid to the astronaut. X is going to be the coordinate along the tunnel, from the middle of the tunnel to the position of the astronaut, and phi is going to be the angle between the vertical line that passes through the center of the tunnel and the radial vector r. So first, let's describe the force of gravity that is exerted on the astronaut. So the force of gravity on the astronaut is going to be given by negative times big G times big M, or big MR, which is going to be the mass of the asteroid contained within the sphere of radius little r, times little m, all over little r squared. So the force of gravity is just going to be given by basically the spherical mass contained within the radius r, which describes the position of the astronaut. So to figure out the mass of the asteroid as a function of little r, we'll note that its mass as a function of little r is going to be given by its total mass times the ratio of the volume of a sphere of radius little r and the total volume of the asteroid. So that's just going to be given by little r cubed over big R cubed, since the volume of a sphere of radius r is just 4/3 pi r cubed, which means that the volume of the sphere is proportional to its radius, so the mass of the asteroid as a function of little r is going to be big R times little r cubed over big R cubed. So if we substitute that in for our expression for the force of gravity, we get negative G times big M times little m over little r squared times r cubed over big R cubed, which is just negative G big M little m over big R cubed times r. So now if we use Newton's second law, we have that the net force in the x direction for the astronaut is going to be the horizontal, or the x component of the force of gravity, which is given by f of g times sine of 5. So that is just negative g times big M times little m over big R cubed times r sine of 5. And now notice that from our figure, r sine phi is just equal to x. So this is just equal to g times the negative g times big M times little m over big R cubed times x. And by Newton's second law, that is equal to the mass of the astronaut times its horizontal acceleration, which is x double dot. So now if we move the mx double dot to one side and divide by little m, we get that x double dot plus big G times big M over big I cubed x is equal to 0. Now this is just the equation for simple harmonic motion, whose angular frequency, omega, is given by the square root of big G times big M over big R cubed. Now the time it takes for the astronaut to go from one end of the tunnel to the other end of the tunnel is just going to be given by the period of oscillation divided by 2, since the period is just going to be the time it'll take for the astronaut to go from one end of the tunnel and then back again. So if we divide that by 2, we get the time it'll take to travel one way. And we know that the period is 2 pi over omega, so we get 2 pi over 2 omega, which is just pi times 1 over omega. So our final answer is pi times the square root of r cubed over big G times big M. Now notice that our final answer does not depend on theta, which means that the time it takes for the astronaut to travel through the tunnel does not depend on where the tunnel is placed. So it'll take the same amount of time for the astronaut to travel through the tunnel, through this tunnel, as it will take for the astronaut to travel through a tunnel that goes through the center of the asteroid. Now, part A of the problem, we know that since the motion of the astronaut is governed by simple harmonic motion, then we can describe its position as a function of time as the amplitude of its motion, x max, multiplied by cosine omega t, since the astronaut is going to start at one end of the tunnel at t equals 0. So at t equals 0, the astronaut is going to start at x max and move in simple harmonic motion. Now, x max is just going to be half the width of the tunnel. So from our figure here, we know that by geometry, x max is just going to be equal to the radius of the asteroid multiplied by sine of theta, since this total angle here is going to be theta. So we have that this is equal to r sine, sorry, this shouldn't be theta. This angle is theta, so this angle here is just theta over 2. So this should really be r times sine of theta over 2. So we have that x is equal to r times sine theta over 2 times cosine of omega t. So the velocity of the astronaut is going to be given by x dot, which is just r sine of theta over 2 times sine of omega t. Since the radius of the asteroid is constant, and theta is also a constant, so sine theta over 2 is a constant. Sorry, there should be a factor of omega due to the chain rule. Alright. So now note that sine of omega t falls between -1 and 1, which means that the maximum value, the max, so this is the maximum speed of the astronaut, is going to be equal to omega r times sine of theta over 2 And since the astronaut is moving in simple harmonic motion, then the maximum speed of the astronaut occurs when the astronaut passes through the middle of the tunnel, which means that the speed v at the middle of the tunnel is going to be equal to v max, which is equal to omega r sine theta over 2. And if you plug in for omega, which we found in part B, we're going to get that our velocity is the square root of big G times big M over big R cubed times big R times sine of theta over 2, which simplifies to square root of big G times big M over big R times sine of theta over 2. So that's our final answer for part A of the problem.